address your question that when we have three variables, we have this relation, this equality. I can rewrite both of these two equations in terms of dot products. You know that the dot product, how the dot product of two vectors in R2 or R3 or in general in Rn is defined. So here I can rewrite each of these two equations in the form of a dot product. So you remember that when we had, suppose I have a vector u, it is a1, a2, and we call them u1, u, and suppose v is v1, v2. As you know, u dot v is defined to be a1 v1 plus a2 v2. And if u and v have three coordinates, are in R3, u dot v is going to be a1 v1 a2 v2 plus what? a3 v3. So
wasn't the one that it becomes zero when they are perpendicular?
exactly, when the two vectors are orthogonal, the dot product is going to be equal to 0. Yes. So I can rewrite these two as dot products. So as you see, the equation on the top in the dot product form will be the equation on the lower left part of the screen, and the second equation, the dot product form, will be the equation on the lower right part of the screen. Now, because of the importance of the vectors that are formed by using partial derivatives, they have a special name in this subject in general mathematics, and it's called the gradient vector of a function at a given point. So again, for simplicity, I have not written xy, but or in the case of three variables, x, y, z. So the vector partial of f with respect to x and partial of f with respect to y at a given point is the gradient of the function at that point.
So you just put the partials in order to get a vector.
Right, we get a sort of vector function. Let me give you an example here. Suppose f of x and y is x squared y. The gradient of f, and as you see on the screen, we use that nabla symbol, sort of inverted delta, for showing, for using as the notation for the gradient. At any point xy is partial of f with respect to x and partial with respect to y. Now, the partial with respect to x, as you know, we view y as a constant. It's going to be 2xy. And for finding partial with respect to y, we view x squared as a constant, so it's going to be what? The partial with respect to y.
Just x squared?
Exactly, just x squared. Thank you. So this gives us the gradient of the function at any point. Similarly, for functions of three variables, we have a similar situation, except we have three coordinates for the gradient. So later I'll discuss geometrically where, the direction of this gradient vector but briefly for now, I'll talk about that later, that if for a function of two variables at a given point, I consider the level curve, we have discussed that on many examples. If the curve you see on the right side of the screen is the level curve passing through a given point, like x naught, y naught is the point of the domain. Suppose this is the level curve passing through x naught, y naught. The gradient, in fact, is orthogonal to that curve. In other words, it is perpendicular to the tangent line at that point. I'll talk about that later, this geometric interpretation. Now we want to, yes, please.
Let me go back to the picture.
Sure.
So what is the surface?
I'm sorry?
What surface?
Oh, that surface is the graph of the function z equals f of x and y.
So it's related to that.
Yeah, it's related because that's the level curve. It is, as you may remember, the level curve is the set of all points, x, y, is such that, so the level curve passing through x0, y0 is the set of all x, y, such that f of x, y equals f of x0, y0. So all of them on that graph have the same height. Now we want to relate the gradient to the directional derivatives. In fact, the question is, in terms of directional derivatives, for a given function of two or three variables, we want to know that in what direction the maximum rate of change happens, and what is the maximum rate of change. So to answer this question, we use the dot product, but in the case of two variables, I can write the directional derivative as the product of the gradient, the dot product of the gradient and the unit vector. As you know, we proved that for the dot product, the other way to compute that is by the formula when we had two and three dimensional spaces. If I have two vectors u and v, I can compute this by normal u times normal v times cosine of theta, and theta is the angle between the two vectors. So here, I can write this by the fact that I just mentioned. And since v was a unit vector, the directional derivative, we computed directional derivative and define it in the direction of a unit vector. Norm of v is 1, so the directional derivative is going to be norm of the gradient times cosine of theta. Yes, question?
Is that like cosine? Why that is cosine then?
Over here?
Yeah.
Because like when I have u and v, as we have seen in the beginning of the class, so this is u, this is v, and this angle is theta. Then another way to look at the dot product is we prove that in fact that this can be computed by this. And theta is the angle these two vectors make. So this answers our question, that this equation at the bottom of the screen, let me write it here. The partial derivative in the direction of unit vector v at any point xy, for simplicity I don't write xy, equals the norm of the vector of the gradient times cosine of theta. So the maximum in terms of theta, the maximum of this product happens where? What is the maximum of cosine of theta? It is 1. Yes. And it occurs when theta is? No, it is 0. For 90 degrees, cosine is going to be 0. So when theta is 0. So the maximum happens. What does that mean that when theta is 0? It means that the angle, exactly. So they show the same direction. So when V is in the direction of the gradient, we have the maximum rate of change. So the maximum rate of change happens when the vector, the unit vector, is in the direction of the gradient. Because then cosine of theta will realize its maximum. And the maximum value of the directional derivative at any point, when theta is 0 and cosine theta is 1, that maximum will be the norm of the gradient. So again, if I have,
So like, we write it in the cosine form just to see when it gets to the
exactly,
maximum?
exactly, we use that equation using cosine to see that when the maximum happens, to find the direction of the unit vector. So if the surface is like that, at a given point, we have the largest maximum rate of change if that direction is the same as the gradient at that point. So please work on this example on your own. You'll see the example. And let me know what you think. Suppose f of x and y is e to the x times sine of y. And I want to find the direction with the maximum rate of change. The given point is 1 and pi. And what is the maximum rate of change? So please work on this on your own. So again, let me remind you the theorem that the maximum rate of change happens in the direction of the gradient. And the maximum rate of change is the gradient at that point. So here for the function, let me also post the solution for you. I'll explain the solution. So the gradient at any point xy for this function, for partial with respect to x, I assume y is a constant, so sine of y is a constant. Derivative of e to the x is e to the x with respect to x, so it's e to the x sine of y. And the partial with respect to y, this time I assume x is a constant, e to the x cosine of y. So the gradient at the given point, it was 1 and pi, the screen. E to the 1 sine pi. Sine of pi is 0. So 0. E to the 1 cosine of pi.
It's negative.
Negative 1, thank you. I made a mistake. What was my mistake? E to the 1, so it's going to be minus e. Thank you. E to the 1 is e, so minus e. In this it is not a unit vector, but for answering this question, it's good enough because it just shows us the direction. In this direction, we get the maximum rate of change. And part 2 of the question, what is the maximum rate of change? The norm of this vector, the norm of the gradient of 1 and pi, which is radical 0 squared plus minus e squared, which is equal to e. So that will be the maximum rate of change. Any question?